Hi everyone, we are Team 4 and our project is face mask detection based on YOLO version 8 and MobileNet version 2. And here is our content. And the first part is introduction.
The COVID-19 crisis shows face mask limits spread, as mask requires identifying uncovered face matters. Two AI models, YOLO VA and MobileNet V2, can automatically detect maskless face. YOLO VA has a new network, anchor-free handler, and versatile loss function. MobileNet V2, a small model of mobile, use stepwise convolution and enhancement like bottlenecks. Comparing these advanced yet different models to detect uncovered face proves difficult. The next page. The primary objective of this project is to experiment with YOLO VA and MobileNet V2 and evaluate their performance in detecting face masks by comparing the precision, recall, F1 score, speed, and resource usage. We aim to determine which model is better suited for real-world applications. Our task in this project is to train YOLO VA and MobileNet V2 on an image data set containing people with and without masks. We explain the two models discussing the methodology, results, and the conclusions. And we go to the next part.
The next part is model principle. YOLO V8 is the largest family of YOLO-based objective detection models, offering state-of-the-art performance. The diagram shows the YOLO V8 network architecture. YOLO V8 is a SOTA model that builds on a success of previous version of YOLO, and its curve feature and chances can be summarized as follows. Next, the MobileNet V2 model is presented. MobileNet V2 is a lightweight network and an efficient model proposed by a Google team in 2018 for mobile and embedded device. MobileNet V2 introduced two improvements to MobileNet: linear bottleneck and inverted residual blocks. Mobile V2 borrows its structure from ResNet using a 1x1 3x3 1x1 structure and also using shortcut to sum the output to the input. Let's to the next part.
Okay. The dataset can be obtained from Kaggle. We collect images of three categories: wear masks, wear masks incorrectly, and not wear masks. The detailed information about the images is shown in the figure below. Okay, next page. Next page. Each picture has unique annotation, which are the coordinates of the mask. After that, we divided the dataset into three parts: train, test, and valid, with partition 0.7, 0.2, and 0.1, and different labels given the 0, 1, and 2, indicated whether wear a mask or appropriate wear of the mask. Next page. The picture shows that the train set result for batch 0 and the valid test result batch 0, which was very high performance as can be seen from the figure. Even the incomplete scene, the model can accurately recognize whether multiple people are wearing masks or not, regardless of whether the face are frontal or sideways. The model can provide a very high confidence scores. Okay, next page. Moreover, here are some curves indicating certain matrix of model training process. The first curve is F1 confidence curve. The curve suggests that the classifier is able to make more accurate prediction as the threshold becomes higher. Next, starting with the precision confidence curve, it appears that the classifier performance is quite good overall. The curve shows that as the confidence threshold increases, the precision of the classifier also increases. This suggests that the classifier is able to make more accurate partial prediction as the threshold becomes higher. In the end, The last image is precision recall curve. Towards the right and end of the curve, we can see that the precision starts to drop somewhat, suggesting that the classifier may be making more errors in its prediction at higher confidence level. However, the recall remains fairly consistent, indicating that the classifier is still able to identify a significant proportion of true positive symbols, even at high confidence threshold. Next page. After conducting the validation test, we collected the data and generated a confusion matrix, which showing that the very good performance of the model. Overall, based on this confusion matrix, it seems that the model is performing quite well in detecting whether people are wearing masks or not, with high true negative and true positive rates. However, there may still be some errors in detecting cases where the person is wearing a mask incorrectly. Okay, next page. In the end, we put the images that we randomly found from the website and the model successful predict result. Thank you.
Okay, so we also use another model for the face mask detection. So another model is the MobileNet version 2. So here is how the model works. So this network is loaded from the Keras application module, and the head is placed on the top of the pre-trained MobileNet base model to create a final face mask detector model. The layer of the pre-trained MobileNet version 2 model are frozen, so they will not be updated during the training process. The model is compiled using the binary cross entropy loss and atom optimizer. And the model is trained on the training data using the fit method from Keras. And here we list some of our workflow and how we use the package and the methods. And after training the model, as we can see in the simplified version of the dataset, that is, the dataset only has the difference between wearing a mask or not. Under this scenario, as the number of the learning iterations increases, the model as a whole develops towards to a better fitting effect. At the same time, we can find that in the test after training, the accuracy of the model can stabilized at about 99%, which is a really high detection effect. But however, we also find some of the limitation of the MobileNet version 2. So our team has conducted several case studies to evaluate the performance. And we found that the detector's processing speed is relatively slow compared with the YOLO version 8. And when tested in a crowded setting, it often fails to recognize faces. But however, in some simple scenarios, such as pictures with only one person or only a frontal face, and the model can accurately identify the presence of the mask with a high degree of confidence. So that's all of the experiment of the model. And next part will be the model comparison.
In order to contrast YOLO V8 and MobileNet, we need to contrast YOLO V5 and MobileNet first, because YOLO V8 is produced based on YOLO V5. MobileNet is a lightweight convolutional neural network that uses stepwise separable convolutions to reduce computational complexity by two smaller operations, depth-wise convolution and point-wise convolution. The depth-wise separable convolutions can exponentially reduce the time complexity and space complexity in theory. However, it is a lightweight model, so although it can reduce the working time, it has lower detection accuracy. YOLO V5 as a model uses new network structures, has high detection accuracy, and it can also reduce the time complexity via hardware acceleration and optimization. Different from YOLO V5, module C3 are replaced by module C2F in YOLO V8, which can obtain more abundant gradient flow information while ensuring lightweight. What's more, YOLO V8 abandoned anchor-based and using anchor-free to find a task-aligned matching method instead of side-length ratio, which helps YOLO 8 improve the accuracy and reduce the training time, as well as make YOLO 8 have a relatively large advantage in prediction speed. In conclusion, YOLO 8 has higher detection accuracy and less training time than MobileNet V2, but MobileNet V2 with a lightweight training model is more suitable to be used for real-time object detection on mobile and embedded devices. Thanks for your listening.